Right, good evening again, class. Sorry about that. Um, Welcome again back to class. Today we'll be doing only past papers, which would be dealing with the topic that was done on Tuesday, which was electromagnetic induction. And just a recap from last week, Tuesday, we talked about electromagnetism, where we said that electromagnetism is magnetism produced by an electric current. How to increase an electromagnet can be done in three ways: increase the current, increase the number of turns, and bring the poles closer together. We also said that the magnetic fields between current conductors, if the current is in the opposite direction, they would repel, and if they're in the same direction, they would attract. And these are the two diagrams, respectively. Electromagnetic induction is basically the production of an EMF of voltage in a conductor due to a change in magnetic field. We talk about two experiments that shows the deflection in the meter, and we said once the conductor is parallel to the magnetic field, it is zero. Perpendicular, you would get maximum voltage, and at any other angle, the voltage would vary to be slightly smaller. Good. Um, we also said how we could increase the induced voltage. You can increase it in three ways: by moving the motion between the magnet and the coil faster. So you move the magnet faster, the coil faster between the magnetic field. Two, the number of turns, increasing the number of turns and increasing the strength of the magnet. There were three laws as well that we spoke about, and three most important are the first law of electromagnetic induction, which says if a conductor is placed in the region of a changing magnetic field, an EMF will be induced in it. Faraday's second law: the size of the induced EMF is directly proportional to the rate of change of magnetic flux. And notice all of these, there must be a change in magnetic flux. If the magnetic flux is stationary, then the conductor will be changing. All right, you would have to move the conductor, or the motion between the conductor needs to change in order to give it to produce an EMF. Good. Lenz's law states that the direction of the induced EMF is always such as to oppose the change that produces it. So those are the three important laws you need to know. We also talk about something called electromechanical devices. There are three types of electromechanical devices. Anybody can name them for me? The three types of electromechanical devices. You can message it in the group chat so I can see. Anybody? The three electromechanical three electromechanical devices. The first one would be we would have done generator. Then we would have done motor, and then we would have done transformers. Good, excellent. All right, and motors and transformer generators operates on Fleming's left right hand rule. The motor operates on which one are the rule? Fleming's left hand. We go down. So Fleming's left hand is for motors. Fleming's right hand is for generators, and the transformer operates on Lenz's law as well. Good. So those were some key points. How to increase the speed of a motor? You can increase it by increasing the current. Use a stronger magnet. Increase the number of turns in the coil, increase the area of the coils. Then we would have related that to two formulas. The formula for generator is E is equals to BLV sine theta, and for motors, F is equals to BIL sine theta. Those were two formulas that were given that not in elective. Good, so that was a recap from last week's class. For today's class, we'll be moving on, continuing for IGC. We would have stopped off from this first question, which was the first page. And this was a 2016 paper, and we would have stopped at this transformer question. Everybody seen this question here? Will everybody get access to this question? IGC students in particular. Everybody seen this? Good. So the question here says, figure 8.2 shows a DC supply connected to the input of a transformer. Good. When switch S is closed, the needle of the galvanometer briefly deflects, then returns to the zero position. Explain why the deflection occurs. Now let me just go back to our notes here. It will be similar to this experiment that was given here, where it said straight wire and a U-shaped magnet, when it is moving up and down, so this is our transformer setup here. Good. So you supply a current here, a DC current. You close the switch. All right. They said in our lecture here, when it is moved up and down, there's a deflection on the meter. Where the deflection shows that there's a current. Also, if you go down lower down to the lecture where we did transformers, what we said about transformers here. Here. When an alternating voltage is applied to the primary side, an alternating current is generated and circulates through the primary windings. The current produces an magnetic field that cuts the secondary, thereby inducing an EMF. And it's similar to this past paper question here. So they say explain briefly why explain why the galvanometer deflects briefly, then returns to the zero position. So simple, we started now for our explanation. We're talking about the switch. So when switch is closed, so you could follow up whoever is the IGC, you could write down the solution while I'm doing it. So while switch S is closed, what happens? Waiting happen when switch S is closed. Current going to flow. So current flows through which winding that is? That's the primary winding. Good. So current flows through the winding creating, producing a magnetic field, or another word for field is magnetic flux. So we are custom using flux. Produces a magnetic flux. All right. That what happens to this magnetic flux now? It cuts the secondary. That cuts the secondary winding, thereby causing and induced voltage or EMF and induced EMF causing an induced EMF that is visible through the deflection of the needle on the galvanometer. Good, so everybody get it? The most important part here for this explanation is that you see that the current produces a magnetic field or magnetic flux, right? That cuts the secondary winding, thereby causing an induced EMF that is visible through the deflection of the needle on the galvanometer. Good? Everybody get this? This is a simplified um, explanation. Remember, it's for 3 marks, so you're not going to write a composition. So it's simple enough so that you could remember it. First thing, when you switch close, what's going to happen? You're going to create a magnetic field. The magnetic field, no current going to flow through the windings in the primary side. As was explained here, that's going to show you back here. So current flows through the primary windings, creates a magnetic flux. The magnetic flux cuts the secondary winding, creating an EMF, and this EMF is shown through the deflection of the needle on the galvanometer. Everybody okay with that so far? This solution? IGC people. Good, nice. So moving on to the next question. So we do this one and then I'll do a CXC question, which is a graph question. So I'll go through to them. So CXC students, you could start this question by the time and then we'll continue it when I come across. So it's the first question you get started, which goes until the end of the year. This is a 2019 question. Alright, for IGC people, we continue. If you notice, IGC students, you have more explanation. The only calculation that you are going to do for this type of questions is transformer calculation. Other than that, you will be required to explain the concept of electromagnetic induction with transformers and so forth. So question 10 now. So another possible question, I believe, was 2016, sorry, November 2016. The question here says, figure 10 shows a wire AB suspended on 2 supports so that it is between the poles of a strong magnet. So this is the U-shaped magnet. If we go back to our notes, so you have an idea. So if you're going back to the notes, your U-shaped magnet is this here. This is a galvanometer. So when you move it between 1 and 2, you get max voltage. 3 and 4, you get no voltage. 5 and 6, you get a small voltage. Good. Question here says, the wire is loose and your power up is supply here, so current flows. You create a magnetic field. The current flows in the direction. Describe and explain any movement of the wire AB when there is a large DC current in the wire in the direction AB. And then there's a large alternating current in the wire. So between AB good. Good. So How are we going to determine this here? We're going to use your a large DC current. So it said a large DC current in the wire in the direction AB. So wire move with current move between AB here. So going from the direction AB, good. So using your Fleming's left hand rule, everybody can remember the Fleming's left hand rule. I'm gonna just go back to it. I'm gonna use the whiteboard to project it. So your Fleming's left hand rule would be like this here. Your thumb is your force or your movement. Your forefinger, if you display them 90 degrees apart as shown in the video Tuesday, here would be your this would be a current flow, which is I, and this would be a magnetic field. Hence the reason we got the formula F is equals to B I L, well, sine theta, right? Well, I will clear that part, but that's just so we're going back again. So here is F, here is B, and here is I. I is a current, as a middle finger. So if you place it in the direction here, let's place the direction of the current here. So between A and B, you're going to have the current flowing. So if you put an arrow between A and B here, so put your finger in this direction here. You're going to place your finger between A and B. Put your finger facing between your thumb finger between A and B. Your forefinger facing between north to south, because your magnetic field always goes from north to south. Your thumb finger pointing direction. So where direction of your wire going to be? Place again. Simple. You place you placing your fingers by the magnet. You're placing your forefinger between north to south, in facing the screen. Your middle finger goes from A to B, so you're going in that direction. So your thumb faces where? You could hide, well, I can message it on the chat, so I'm going to actually get it correct. So if you place your fingers when you displace it like this here in the whiteboard. So this going your eye facing, think about a U-shaped magnet here. I'm just going to draw it here. So this is a U-shaped magnet here. Can do that part. The magnet is between here. Somewhere here. So then, so you're facing the current. We're going to draw back this. So this is your magnet here, and this is your wire. This is your north, this is your south, this is your Y. So you go from A to B. So you're placing your fingers here between A to B, and your magnetic field is between this direction here. Good, north to south. The current goes so. So that means your thumb, if you're going to place it, going to face up. So your directional current should flow. Your movement should be upwards. So you're facing, you're placing your fingers between the magnet. Your thumb finger piece goes between A and B because your thumb shows the direction of the current. The current goes between points A to B. Your forefinger points between north to south, as in the directional arrow here, because this is B. Sorry, this shouldn't be B here. It should be a current flow. Good. And your F points upward. So that means for your answer here, here, it should be, the direction of it should be up and down. So interaction between, history marks, interaction between, interaction of the magnetic field, interaction of the magnetic field, interaction of the magnetic field interaction of the magnetic field between the poles north to south, N to S, and the magnetic field created when current flows from flows through flows through wire um, A to B comma, the wire will experience a force that causes it to move, experience a force that causes it to move vertically upward, upward. Good. So it's the interaction of the two magnetic field. Where get the two magnetic field? The one between the U-shaped magnet, which is north and south, and the next one is when current passes through the wire. Because remember, when current passes through a wire, a magnetic field is generated. So the interaction between these two magnetic fields causes it to move upward, and that was explained last week in your moto explanation here. That's the reason for this to move here, the interaction between two fields. Good. So here, as we said, just going back, since the current flow in opposite direction, the forces produced is also opposite. The two forces in opposite direction constitute a couple which turns causes a turn effect. How you get this turn effect is because the interaction of the magnetic field. When current flows through the wire, it creates a magnetic field, and then you have the permanent magnetic field between the magnets. So the interaction between the two magnetic field will cause it to get a force, and that force would either cause it to, well, in this scenario, upward. Good. And which rule we use for that? We use Fleming's left hand rule. Good. To explain that. Everybody okay with that? The answer? IGC students? Good. Nice. So that's the answer for that one. Let me go back just to make sure I make no grammatical errors. It's the interaction of the magnetic field between the poles N to S and the magnetic field created, sorry, when current flows through wire AB, semicolon, the wire will experience a force that causes it to move vertically upward. Showing from your screen here. I'm just going to go back to your share screen. Showing from your screen here, when you place your finger like this, 90 degrees apart from each other, between A to B, current flows between A to B, that's your current direction. N to S is your magnetic field as your forefinger, and your thumb would point upward, which is your force. Good? Nice. So they talk about an alternating current now. A large alternating current in the wire. So what's going to happen is now, when I pass a large alternating current, it's going to have the same reaction. The only difference between the alternating current now is that the direction of it would move which path? The force of it going to move upward or down? What do you think? Hmm? Now, direct current causes it to move upward. Alternating current, just referring back, so from your whiteboard here, what should I say? So for DC, we learn that DC voltage, for DC voltage, your voltage line going to be like this here. Then, so the ammeter is only positive. And for a positive in the magnetism, it went upward. Good. Now AC is slightly different. AC, we know that the fields fluctuate, hence the reason we have frequency. So you have both a positive and a negative direction. So that means what's going to happen to the wire? If the DC only had positive and it moved up with the AC, what do you think going to happen to the wire? Huh? You're going to move up and then you're going to move down. Then this is movement of wire. I'm just going to put this as F here. F here force. So when you have a force with the EC, you're going to have it moving up and down because why? In the positive cycle, you're going to move up. When the frequency dips in the negative cycle, you're going to move down. So your wire is going to be toggling between. If we go back to our notes, everybody good with this whiteboard so far, so I can move on or leave it a little bit. I can remove the board. Hmm? Good. So for DC, it went upward. The force was upward. AC now, we expect it to go up and down because you have a positive side and a negative side. If you go back to your notes here, your notes would have shown that when we was going through this experiment here, for this one, how we are going to get the maximum voltage. So when it is moved up and down, there's a deflection of a meter. So your voltage is going to cause it to move up and down here. Maximum between 1 and 2. This is when you have an AC voltage inside of it. Good. So here the interaction, so we can simplify interaction, your explanation, sorry, that is interaction between both magnetic fields. Which is the two magnetic field? The magnetic field of the current flowing in the wire between A and B, and the magnetic field of the magnet between north to south. Those are the two magnetic fields. So interaction between both magnetic field causes or we should start it like this here. When a large AC current flow in wire comma the interaction between both magnetic fields causes the wire to move vertically upward and downward. Good. The reason, let me just explain the reason why I had given you 3 marks here before. The reason why they would have given you here 3 marks before is because they wanted you to explain where you're getting 2 magnetic field in this here. The 2 magnetic field was the interaction of the magnetic field between the poles north and south, and the magnetic field created when the current flows through wire A and B. So you have to explain where you get the 2 magnetic field from. That's where you get mark for. Then you talk about the wire experiences of force and the direction of the force. In this scenario here, we did not have to explain that anymore in part 2, because why? We talked about the magnetic field before. You see, when a large AC current flow in the wire, the interaction between both magnetic fields cause cause the wire to move vertically upward and downward. And this would be similar because why we using same Fleming's left hand rule for this. Good. So we know that it will move upward and downward because the current keep moving from positive to negative because of frequency. Everyone okay with the explanation for it so far? IGC students. Good. So, right, so we can move on. So for the IGC students, you can start doing one with our calculation. Try this one here. For IGC students, you're doing this question here for me. It looks like this. Number 1, that's actually page 12. So IGC students, start on page 12 and 13. Page 12 to 13. Again, CSEC, so we're gonna start with, so you could work on it. Your question looks like this. You can do this small explanation as well. Remember, the explanation is exactly what we did. All the explanation is going to be around the same. You could shorten it based on the number of marks awarded. Then, so we're going to continue. So the CXC students, we're going to work on this one here. So here what the question says. Figure 1 is a diagram of a transformer. Label the parts X, Y, and Z. Then, so your X is labeled as, this part here is your primary side, so that's the primary winding because you point to the winding itself. So for here is your primary winding, so X is labeled as your primary winding. Y is your what? Secondary winding. And Z is your what? Your core of your transformer. Good? That's where you put the windings around your core. So that's the three parts. Your core, your primary winding, your secondary winding, and the core or iron core or steel core, whichever one it be. Then the core be transferred. Moving on, IGC CXC students, I get this so far. Let's see who are the CXC students that here. Angelina, Shauna, and Regan. You all got that so far? Alright, good. So 2 of that 3 so far. Alright. So we're moving on. So here the question says, excellent. So the question here says, the transformer shown in figure 1 was tested and the values for the primary voltage VP versus VS were obtained. The data is shown in table 1 below. Using the grid on page 7, plot the graph VS, VP and determine the gradient S of the graph. Good. So it's VP versus VS. So VP would be on your Y and VS on your X, right? So let me just label that here. So this is your Y and this would be your X components. Let me just make sure. X. Alright, so we have to plot the graph. Well, I don't even know how I'm gonna plot this graph here. We'll see how we can plot it. Let's see if I can. Right, so well, they are plotted. So for the CXC students, I don't know how I plot this thing, but I'm gonna use a shade screen. See if I can do it. Good. So we're gonna plot the lines like this here, where we'll have VP here and VS here. Your gradient obviously going to be S is equals to Y2 minus Y1 over X2 minus X1. Good. So you're gonna plot the graphs. We're gonna create a scale. You're gonna have your graph plot, which is VP um, versus VS. Then your VP, your scale. Let me say appropriate scale for this here. Your scale should be around. So for the VP, we could use. Let's see how much here. We could use around 8. So sorry, not 8. So for the scale, we could use the scale of here. We could use every 1 centimeter. So we could use a scale of your scale on y-axis 1 centimeter is equals to, we could say 1 volts. We could call it 1 volts or 2 volts. 1 volt, right? And on x-axis on x-axis 1 centimeter is equals to um, let's see, we could get 1 centimeter is equals to 10 volts. To get that around 10 volts, everybody can do that. So 1 centimeter is equals to around 10 volts. Good. So we're using them to scale and we're drawing the graph. VP versus VS. So you would obviously have things here. And then when you plot out the points, you should get a straight line graph. Remember, you're not starting from 0. So obviously, the graph should be like this. Between here. No, another draw straight line. Then something like that. Right. So for the CXC students so far, um, somebody could just tell me the gradient that I get. Let's check it out also. Right. So anybody did that so far that I could share it the graph. Sorry, that I could share it. Any CXC students did the graph so far? All right. Somebody give my answer for the gradient already. Anybody else? So this should be V. S on V2 here, which is X versus Y, right? Right, so Sean and Regan, you all did the graph so far? So anybody else, the CXC students, anybody else got through? You could use 1 centimeter to oh so high fingers out high that's all I see. I don't have a graph paper with me right now. Okay, instead of using 10, we try using 5 for some people to here. And here could be 0.5. Let me try let's see if I can get a graph paper to use so I can send all the image. Regan, you got any answer? Alright, I'm not get some graph pages, so give me about 5 minutes or something and I go draw the graph. For the GC students, I hope you're getting through with the past paper question. Right. Right. Actually, I'm gonna post up for these IGC students. Um, I'm going to post up a solution on the group chat. The graph, sorry, so you could just check for the graph. Right, so for the CXC students, just pay attention to the graph. Everybody seeing the graph? The CXC students, that's the graph solution. For everybody should get. Everybody seen it? Good. So we are going to see the graph. So the graph here is as follows. Um, so your graph should look like this. So I'm going to everybody see the shade screen on the graph? Right, so your graph with your VP on your y-axis and on your x-axis you would have your VS. Good. Your plotted points, you would not get all the points lining up together, but as was explained previously in class that you take the best fit straight line graph and then we're going to do the gradient for it. So this is your graph here, where 0 is the starting point here. Obviously, a line, you're not going to project it to the 0 because it didn't give it those points. So from your, everyone seeing the shared screen with the graph, right? Good, nice. So you plot your graphs, VP versus VS. And well, in this scenario, VS versus VP, X on your VS on your x-axis and VP on your y-axis. They ask you to calculate the gradient. So how we calculate the gradient? Your gradient will be calculated using. Well, I have drawn a triangle here, so we could use this triangle data. So from the shared screen, your gradient, we're going back to the gradient. So your gradient would be S in this scenario because they give you S in the question. S is equals to y2 minus y1 over x2 minus x1. Now if you go back now, y is your VP values. So you're going to VP to VP minus VP2, VP1, sorry, over Vs2 minus Vs1. Those are the 2 points with Vp on Vs. I'm going to use a triangle value that I had used from here. So this is your Vp value. So you would use 8 and 5. So we could use 8 and 5. Now remember, all the answers going to be around the same. It wouldn't be exactly the same. However, it will be similar. So it's going to be 8 minus 5 because at the top of the triangle that I use. Over, if we go back to the drawing, so the drawing here we had the lower part of the triangle, which is here. So we got 8 from up here, then we got 5 from here in the triangle, then we go lower down, which would be 72, and then we would have 45. So 72 minus 45 from the graph, the lower part of the triangle. Good. So here would be 72 minus 45. 8 minus 5 is 3 over 72 minus 45. 27. So 3 divided by 27, you'll get 0.111, or we could have 1 over 9 if you want to use it as a fraction. If you prefer to use it as a fraction, is okay. So I'll just simplify the fraction before we go to 0.111. So it will be 1 over 3 into 3, 1. 3 into 27 is 9. We could use it as that, or if you prefer to break it into simpler terms, you're going to be 0.111. Good. So CXC students all understand how we get the gradient? Good, excellent. So Angelina was correct with her answer. Shauna, you okay with this so far? You would have gotten 9 because you would have put the VS value on the VP value, which you would have looked at it differently. So the calculations would have been wrong, but the graph might have been similar. Um, so, but you're okay with the how we calculate the gradient so far? Shona and Regan. Good. So that's the calculation for your S value. I could take off this on my screen now. Good. So that was the S value. We're going to do now your, that's your graph value. So 4 marks to that, 1 over 9 or 0.111. We're moving on now. They say use the gradient S to calculate the number of turns. Now, the gradient of S, let me go back, the gradient S, let me go back to the whiteboard, um, to our notes firstly. So from the notes here, we would have learned that when I had explained last time, I had put in a value here. The value was TR. TR is the transformer ratio. And transformer ratio is VP on VS. So what does the S represent? Your S represents something called transformer, your transformer ratio. That's what your S stands for in this calculation. Good? Which is VP on VS. If you notice, if you go back to the whiteboard, um, here our calculation was always VP on VS. Good. So it's P on S, so VP on VS, so that's the transformer ratio. That's what S stands for in this scenario. Good. So they ask us now later down in the question, for CXC, the number of turns in the secondary is NS, given that the number of turns in the primary is 85. So what's the formula for the transformer ratio? If we go back again to our transformer ratio, in the transformer ratio, we said that well, S or TR, S is equals to VP on VS is equals to NP on NS is equals to IS on IP. Now, we are only concerned about this one, your NP, so we're going to remove, we're going to remove all the others. Good. So S is equals to what? NP on NS. What was the S value? Your S value, if you want to use it, 1 over 9 is equals to NP. How much NP was? NP was 85. And your NS, we don't know the NS value. So we need to calculate the NS value. What was the NS value? Your NS value, we do not know that. So we could transpose this here. Good. So let us say we transpose in that now. We take the NS and we carry it up. So it's going to be N. So this goes up and this goes up on this direction here. Good. So NS is equals to 85 multiplied by 9 over 1 because it's taking the 1 and carrying it underneath. So NS is equals to, how much you think NS is equals to when you use a calculator? Work it out and see what you get by the time. What I get for NS? Just 765. Good. So 765 should be an answer for that. So it's 765 and your unit for that going to be turns. Good. Because your transformer ratio is given in turns. So the transformer is basically, it goes from a lower voltage, sorry, goes from, let me go back here. So you can see for yourself, it goes from a low voltage to a high voltage, which means that what type of transformer is this? If it goes from low to high, if you go back to your notes, so just going back to your notes here. So if you go from a low voltage to a high voltage, you increase the output voltage as a step-up transformer. So you have a step-up transformer, right? And they say has more turns in the secondary. We went from 85 turns in the primary to 765 turns in the secondary, which means it's a step-up transformer. Good. We're moving on to the question now. So that's another 4 marks. So the question here says now lower down, calculate the current in the secondary if the primary current is 1.8. So we're going to use back the same formula. So we're going to use back the same formula here. I'm going to clear everything here. So the formula we know would be S is equals to VP on VS is equals to NP on NS is equals to IS on IP. Remember the current is different, right? So we're going to put 1 over 9. So we're going to eliminate all that we do want. So you usually erase, well, my scenario is the same. Good. So your formula now becomes S is equals to IS over IP. So you're going to be 1 over 9 is equals to, we don't know what IS is, but we know that IP, if you go back to the question, here, IP is how much? They said that IP is 1.8 amps. So we're going back to IP, which is 1.8 amps. So IP is 1.8. Good. So we're going to transpose this. You take this and you carry it up, and you leave IS as is. So now it's going to be 1 multiplied by 1.8 over 9 is equals to IS. So when you work it out in a calculator, how much you get? It's going to be 1 multiplied by 1.8 divided by 9. Your answer should be of this part here. Your answer for IS should be equals to 0.2 amps. So I had explained this earlier. We said chooses, or I said that if in your power of your transformer remains the same, if your voltage increase, that means your current will decrease. In this scenario, voltage went up. It went it went up by a factor of 9. Good. So your current obviously going to decrease by a factor of 9. It went from 1.8 to 0.2. Your voltages went from just using from 1 volt to 9 volt. Your secondary windings went from 85 to 765. So everything went up. Your voltage will go up. Your number of turns will go up, but your current will go down. I was explained as to maintain the power of your transformer. S is equals to I multiplied by V, which means that the power of the transformer is the same. So if your voltage goes up, your current will have to go down. Good. So your answer is 0.2. Everybody, all IGC students get it so far? Good. Excellent. So your answer is 0.2. Shona and Regana, Angelina, are they okay with this so far? Good. Excellent. Nice. So we're moving on to this lower part here. The question here says in part 3 of the question. So after this, we'll take a break. When we come back, we'll take a break from 6:30. When I come back, which will be 7, we will do 2 IGC question, 1 CXC, and the balance they could do for homework, right? Which will be 1 question each, I assume. Right, they said in question 3, the power output P out of the transformer. Calculate the power output of the transformer given that the voltage in the secondary is 55. So if your voltage in the secondary is 55, good, mine is 55 volts, how are you calculating power? And I've given you this formula because I just explained it. Your power formula, all right, so your power formula, we would have learned S or P out in this scenario is equal to voltage multiplied by current. S is V by I. So we said that your P out, I'm just going to erase the change the formula. So P is V by I. We would have learned that. So P out is equal to Vs multiplied by Is. We're taking it from the secondary side. Remember, the power is the same. So if we use the primary or the secondary, doesn't matter. But because they give you a secondary voltage here, you're going to use the secondary side. So your P out, we don't know what it is, but we need to calculate. They say secondary voltage was how much? We go back to the notes. Your secondary voltage is 55. Good. So the secondary voltage is 55. Good. So 55. And what was your secondary current we calculate? 0.2. Good. Because we're using the same gradient of the graph. Good. So 55 multiplied by 0.2 is how much? Let me see. 11. Excellent. So we get 11. So your answer is 11. And in this scenario, it will be considered as volt amps, or we could say it's watts in this scenario. Good. Good. And that should be your answer. Everybody okay with that so far? But CXC students in particular. Good. Excellent. So recap. So when we come back after break, we should be here back by 7. IGC and CXC students, you could start this one by the time. This is the second question, which is pages 5. This whole question we're going to do is drawing a graph again and a small explanation. So wait, all of this is one question. So, so um, let's see if we could do that one. Or we didn't do any magnetic field one, so we could do this one here. So CXC students, we're going to do this question here, the one with the magnetic field, because I never had done a question with you, even though we touched on it last week. So we do this one here when we come back. And for IGC students, we continue this question and we'll do another one. Okay, so we'll go and break and we resume. We resume class 7 o'clock. So half an hour break. So 7 usual. So we're going 7 to 8, right? So resume class at 7. Good, enjoy the break, and I'm see you back at 7 to finish up some more past paper questions. Very good. So continuing from break, everyone here? Anybody? All right, good. So far that's one person. The others. Nice. So free IGC students, so only two CXC students alone reply. I'm concerned about the IGC because obviously the IGC that's what we're going to deal with now. So CXC students, you're going to focus on this question 6 here. Question 6. And these two parts are the whole 2018 question. So we're going to focus on that now. CXC students, you could work on that whilst I focus on two questions with the IGC students by the time. Good. So IGC students, back to you. So the question here says, if you turn to the lower down, that's page 12 of the whole document. It says, figure 8.1 shows a bar magnet suspended by a spring over a coil. The coil is connected to a sensitive center zero millivoltmeter, which means this center zero millivoltmeter basically always goes back to zero regardless of whatever reading it gives, whether left or right, it goes back to zero. Then so they said this is a sealant spring connected and a magnet here. There's a coil connected to a millivoltmeter. The lower end of the magnet is pushed downwards. So what happens is the magnet goes downward into the coil, and the upper end of the coil into the upper end of the coil and held at rest. During the movement, an EMF is induced in the coil. The meter shows the deflection to the right and then returns to zero. Explain why this EMF is induced. This basically goes back to our, if we go back to the production of an EMF, which is electromagnetic induction, they said the production of an EMF in a conductor due to a change in magnetic field. So why is the EMF induced? Is because the magnet, when placed in the coil, the the EMF is produced. And the same here. We just take for example this second one where it says biomagnet coil. When the magnet is pushed into and pulled out of the coil, the meter shows that a current is induced in the coil in one direction. As the magnet is moved in the opposite direction, move out. So the deflection occurs because of the movement between the coil and the magnet. Good. So we go to Faraday's first law of electromagnetic. If a conductor is placed in the region of a changing magnetic flux, an EMF will be induced in it. So to answer your question here, the question here says, explain why the EMF is induced. Um, because why the EMF is induced? Because um, the coil because the magnetic field magnetic flux from the magnet cuts the coil cuts the coil conductors, thereby creating thereby inducing using an EMF. So if we go back to Faraday's law of first law, that said if a conductor is placed in the region of a changing magnetic field, an EMF will be induced in it. And that's exactly what we say. Explain why the EMF is induced is because the magnetic flux from the magnet cuts the coil conductors, thereby inducing it. Or you could say the coil conductors was placed in the magnetic field. Remember, the magnetic field from the magnet here is stationary. This is stationary. However, what causes the magnetic field to change is the motion up and down. Your coil is stationary, the magnetic field in the magnet is stationary. However, when you move it, it 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 seems to be a change in magnetic field, which is what causes the EMF. So explain why this EMF is induced because the magnetic flux from the magnet cuts the coil conductors, thereby inducing an EMF. Good, with these word cuts, so you could clear easy the word cuts. Simple. Alright, so IGC students, you all okay with that so far? Everyone? IGC. Good. So lower down it said now, state what happens to the needle of the meter when the magnet is released from rest. So let me go back to the top. They say when the lower end of the magnet is pushed down during the motion, an EMF is induced in the coil and it deflects to the right. So when it goes down, the meter goes towards the right. What they're gonna expect if the magnet is released and moves back up, released and pulled back by the spring. The meter, what's gonna happen to the meter? If when you push down the magnet, it moves to the right. When you release the magnet and it moves back up, what's gonna happen to the meter? How are we gonna move? The meter gonna deflect backward, which is going to be in the opposite direction. So the meter deflects to the left and returns to the zero position. No, let me just explain. When they said right, what happened is the meter itself deflects towards the right momentarily. So you go towards the right, and when the magnet stay inside the coil, it goes back to the zero position. The meter goes back to the zero position. That's because the magnet is inside the coil. However, if you let go the magnet or when it go back upwards, the meter going to deflect in the opposite direction, which is the left hand side. You're going to deflect on the left hand side and then return back to the zero. Good. So here when you push it downward, it goes towards your right, and when you let it go and then move back upwards, it goes towards the left. That's because of Lenz's law. All right. I'll explain that. So the meter deflects to the left and returns to the zero position. They said now if the magnet continues to oscillate up and down. So what if the magnet moving up and down now inside the coil, moving in and out of the coil with each oscillation? What's gonna happen? What do you think going to happen? They say the magnet continues to oscillate up and down, moving in and out of the coil with each oscillation. What do you think going to happen? The meter will deflect from left to right, from left to right. The meter going to deflect from left to right. Good. It wouldn't it was center but momentarily. You go to the zero position but momentarily. But if it's moving up and down, you're going to keep be fluctuating from left and right, left and right all the time. Good, so everyone okay with that so far? Good, nice. So we're moving on now to lower down this question. Here what the question says, part B. Figure 8.2 shows a transformer. So have a transformer 240 volt means is a AC because the symbol here. 800 turns, your lamp is 6 volts at the end. So you go from 240 volts to 6 volts. 800 turns. They said the primary coil is connected to a 240 mains. Secondary has 8,000 turns already. Secondary is supplies a 6 volt lamp. Calculate the number of turns in the secondary coil. How are we going to do that? Good. So we're going back to the formula, the transformer formula, which is Vp on Vs is equals to Np on Ns. What is your Vp value? Primary voltage. The primary voltage was 240. What was the secondary voltage or the voltage of the lamp? What was the voltage of the lamp in the question? We'll go back to the question here. Your voltage of your lamp in the question was your voltage of your lamp in question was 6 volts, so that's your secondary voltage. So 6 volts is your secondary voltage with your primary turns. Your primary turns is 800. That's on this side. This side is your primary here. Wait. Here is your primary, which is 8,000 turns, and we don't know the secondary one. We are asked to calculate the secondary. So your primary is 8,000 turns. We need to calculate NS. How are we going to calculate NS of the secondary turns? We're going to transpose for that. You're going to carry this on top, carry this downward, and carry this on top. Good. So your new information. So which is NS now. So we carry that on top. So it's going to be NS is equals to 8,000 multiplied by 6 8,000 multiplied by 6 divided by 240, right? Gosh. Right, so it will be NS is equals to 8,000 multiplied by 6. We can carry 6 on top divided by 240 exchange values. So how much I get for NS? Remember, VP was 240, VS was 6. So we expect that if NP is 8,000, NS is going to be less. Alright? So we just had a calculation. So it's going to be 8,000 multiplied by 6 divided by 240. So your answer is 200 turns. So if you notice, we decrease. Why? Because you go from a high voltage to a low voltage. Plenty windings to a little bit of winding. So that means it's going to be reverse for the current. Your current is going to have to be high. Let's take that into mind. Everybody get us so far? That's working so far? Good. Okay. Right. So NS is 200. Good. So that's the for the first part. So your answer for that is 200 turns. Nice. So we're moving on to the next question, which is we just see. Right. So it's still low. I don't know any question. So NS is 200. They say the primary current now is 0.05 amps. Calculate input power. How are we calculating input power? Formula for power we would have done this Tuesday. So going back to the whiteboard again. So we're calculating power. P is equals to V multiplied by I. So input power means that you have your primary voltage multiplied by your primary current. Your primary voltage was 240 volts. Your primary current is how much? 0.05 amps. So when you work it out, is how much? 240 by 0.05. What we get? 12 watts is the answer. Everybody get that so far? Everybody see how we get that? Any questions on that so far? Okay, good. Nice. Only one person replying here. The other side, nobody not even replying from it. Let me know if you're okay with it. Alright, so we're moving on to the next part of the question here, which is so we calculate the input power, which is 12 watts. So here we get 200. Am I right on that? 200 turns. Here is 12 watts. Those were the answers we get. Right. They said now the 90% of the input power to the transformer is transferred to the lamp. Calculate the current of the lamp. So if your power, they said now, which means some of the power is lost. So that means 90% of the power is on this side. So your P out is 90% of the value, and they ask you to calculate the current of the lamp. So we just go back to the whiteboard. So here, so we know that so P out, they say that P out is equals to 90% of your P in value. So you're going to be 90% of 12 watts. How much we get so far available for the output power? So you'll be 90%, 10.8. So I get 10.8 watts available for the output power. Alright. So if that's the output power, they said to calculate the current of the lamp. So we know that we go back again. P out or P is equal to V multiplied by I. You want your secondary current, that's the one going to the lamp. Your secondary voltage is voltage of the lamp, and your P out is what we just calculated. So we want to find a secondary current. How you find a secondary current? If we transpose this equation, IS is equal to P out divided by Vs. So your P out was 10.8 divided by your Vs. What was the voltage of the lamp again? Let me go back to see. Your voltage of your lamp was, if you come back here, your voltage of your lamp was 6 volts. So you go back, it's going to be 6 volts. So divide by 6. So your secondary current IS is 10.8 divided by 6, which is 1.8. See if I get an answer for me. Which is 1.8 amps. Good? IGC students, are you okay with that? Yeah, only Dimitri alone answering. Anybody else? Good. Okay, everybody drop out of this group. Okay, good. So IGC students, all you good with this, right? Could you raise? Nice. So we're good so far. We continue with this now. So your current here we got it as 1.8 amps. Good. Right, let me go with this question here, IGCC. We'll do this one more question and then I'll do one for CXC and wrap up for tonight. Good. So the question here says for IGCC student, the output of an AC generator in a power station is 5,000 volts. A transformer increases the voltage to 115, which is 115,000 volts, before the electrical power is transmitted to a distant town. State and explain using a relevant equation one advantage of transmitting electrical power at high voltage. Why do we transmit electrical power at high voltage? So that, and I had to explain this before, so that the current flowing through the cable, the lines, the power lines would be very small to prevent insulation breakdown, arcing, overheating of cables, overheating of lines or power lines, overheating of power lines. Right? Good. So that's the reason why we transmit power in high voltages, so that they could have very small currents or low currents. Good. So that the current flow would be very small to prevent insulation breakdown. That's the major reason. Then overheating of the power lines and then arcing. Good. How we could show this through our formula, because that asked us to use a relevant formula. We can use this formula here from the transformer ratio, and I explained this last time. We could use this formula here, um, VP over VS is equals to IS over IP. Then, which means that if your current goes up, your voltage go up, your current must go down, and I had explained it through the formula P is equals to V multiplied by I, and I said that if your input power for your primary current and your primary voltage, if your voltage increase, for your power to stay the same, your voltage must decrease. Good, and vice versa. If your power is the same, and your output wants to, let me label this, sorry, I'm gonna take off this IP part. It should be S. If you want your current to go up, then you're going to drop your voltage. That's a P to remain standard. So you can write down the formula. These two formulas come out from this set here, which means the same thing. Good. So that ask you for a formula to back it up. So that's the formula that you are going to use. So when you're done, take down that here, let me know, which means that your power stays the same always. But if you move in your voltage and your current, if one go up, the other must go down in order for the power to remain the same. Good. So P is equals to I multiplied by V, or V multiplied by I in this scenario. Everybody okay with this so far? The screen before actually change it. Good. So just going back to the last here. So the question here again is state and explain use a relevant equation. One advantage, so I've given you three advantage of transmitting it at high voltages. One, to prevent insulation breakdown, arcing and overheating of power lines. Those are three different advantages. So I'll put it as one. So if ever you remember one, that's okay. Alright, so the question here lower down in part B of the paper, it says the transformer contains two coils, the primary coil and the secondary coil. State the other main component of the transformer and the material from which it is made. We talk about this because we just did this in CXC, and these are your answers here. So the first thing we'd have the primary coil or the primary winding, and then what? So after your primary coil, your primary winding, you would have had your core. So as the third component in any of these transformers, there are three things, actually four, but we only considering these three because the fourth one is something called enclosure. You would have to cover it up so to protect the windings. So the state the other main part of the transformer, which is the core. Your answer should be the core. Core and is made up of iron, or you could say steel. Good. Because you have iron, you could put steel, and there are plenty other components. Good. This is state the component in the transformer to which the AC generator is connected. So where is an AC generator connected in this transformer? In any transformer. After it generates, so state the component in the transformer to which the AC generator. So think about it. Well, I'm not sure if I'd explain this. Yeah, but when electricity is produced, there are two government companies that produce electricity at the moment. PowerGen, the next one is TGU. When they produce electricity, they produce it through something called turbines. When they produce it through turbines, they connect it to transformers to step it up to a very high voltage of 132,000 volts or 220,000 volts, and then send it down the line, the power grid. So your generator is a turbine. Alright, so you generate the voltage. After you generate the voltage, you gotta connect the transformer to it. The transformer would be connected to which part of the generator? The generator would be connected to the primary of the transformer. Good. So that's correct, Dimitri. So your answer is state the component in the transformer to which the generator is connected, and it will be the primary coil. Good. You connect to the primary coil. So, and the output of the transformer is sent down to the electrical grid. Good. Moving on. There are 400 turns on the primary coil of the transformer. Calculate the number of turns in the secondary coil. So let me just see. You went from 5,000 to 115. So I get back the whiteboard. So your VP, your primary voltage was 5,000 volts, right? You generate it, then you connect it now to the transformer connected at the ending of the transformer, you get 115,000 volts. Good. They ask you to find the secondary current now. Your secondary turns, if your primary turns is 400. So that asks you to calculate this. So NP is the number of turns in your primary coil, which is 400. They ask you to calculate NS. So if NP is 400, So we know that NP is 400 turns. We're going to calculate the formula now. We're going to use the formula to calculate this. And the formula we would have learned was Vp on Vs is equals to Np on Ns. What was the Vp value? Vp value was 5000 over your Vs, which is 115,000, is equals to Np was 400, but we don't know what Ns was, so we need to calculate Ns. So we're changing up this value here. You're carrying this on top, you carry this underneath, and you carry this on top. So you're going to be Ns is equals to 400 multiplied by carry the 115 on top, so it will be 115,000 over you carry the 5,000 underneath where the NS was. So divide by 5,000. So NS value is equals to, so going to be 400 multiplied by 115,000 divided by 5,000. So your answer for NS, anybody can tell me what was the answer they get? Just work it out and see what answer I get from it. Let's check back. So right. So they said in the question here, just projecting the screen for you to see. The question here they said the primary coil. So the output of the generator is 5,000. So the output is basically the primary side, which is 5,000. It goes into the transformer, increase it to 115,000. Right? And then send down to the electrical grid. So you went from 5,000 to 115,000 at a current of windings of, let me see the windings. Your windings was, you went from 400 to another number. We don't know what was the other number, so we're going to calculate it now, which is when we calculate it, I would have gotten, I think, well, again, 9,200 turns. I just confirm that everybody get that. So your 400 is the number of turns in your primary. So we're going back again. How are you going to, VP is 5,000, VS is 115. So you went from 5,000 to 115 in transformer. You went from 400 turns to a higher number. It has to be a higher number. So you carry the 115 up by the 4,000, the 400. So 400 by 115 divided by 5,000. So you switch those two. So again 92. Everybody get 9,200. IGC students. Just confirm. So yes, good. So everybody get it. So we're moving on. I can move on to the next question now. Good. So here was 9,200. 9,200 turns. Then, right, they say part C. Transformers within the town reduce the voltage to 30. So it went now, when it go on the electrical grid, it coming into a village, it went from 115,000 volts now to 230 volts. So just one reason for this. Why you think we break it down into a small voltage? Why you all think we break it down into a small? Remember, we transmit it at a high voltage because we wanted only a small amount of current to go through the line. Now we change it in a small voltage. So what do you think we want? What do you think gonna happen to the current? what the current going to go up, it would increase. Good. So the reason is to increase the current to supply the town. To increase the current load, the to increase the load current to supply the town, the entire town. So you reduce the voltage, so you're gonna have plenty current for everybody. Because as was explained, when we do house wire and we do it in parallel, your voltage is going to remain the same. The only thing that you are going to take plenty is your current. So you want more current. How are we going to get more current? You use a small voltage, so your current going to increase. To increase the load current to supply the town. Good. So IGC students, you all okay with this so far? Good, excellent. So what you could do for me for next week, you could do this question here. Um, this question on the sheet. All IGC students are doing page 16. So we work on this next week before class start. So you're going to do pages 16 to 17. If you want, you could wait on and watch the question that they're going to do with CXC, because it's the same answers basically. All right, so you could do that for me, and it should be good. So just page 16 and 17, you're going to focus. Page 16 and 17. This would include this part of the question too, eh? The whole 16 and 17. Yeah, that's it. Even though it's a different question, that's nothing. Still do it, right? Good. So that's for your homework here. IGC homework, pages 16 to 17. We're going to focus now on the CXC students. For the CXC students, now back again. Right. So we on with this question here, which says figure 6a shows figure 6 shows the magnetic fields between poles. Remember, your magnetic field lines always go from north to south. Say arrows always going to be going from north to south. Complete the following diagrams to show the magnetic field due to the current conductor in the current is directed into the plane paper. So what's going to happen? Remember, you're going to have concentric circles. So if it's going into the paper, we're using the Maxwell screw rule. So if it's going into the paper, that means you're going to put your thumb like you're going into the paper and turn your hand with your cuff showing in any direction. So you're going to have concentric circles like these. Again, so your circle is going to be that, and they're going to be going in this direction here. Good, so you're going to completely draw in like that. You could draw about 3 concentric circles for them for this here. This is all asking for so far, just for you to show them the lines. So you're just going to draw those lines here. All right, which is the same thing we just see. So you're okay with that, right? You're drawing it on the sheet. I couldn't draw it on the sheet, so I drew it on a separate board. X means going into the page or into the board, as in this scenario. The circles must be uniform. Well, I don't have a compass here, so I just use whatever I have here for now. Good. So CXC students, you all okay with that? I just want to know before I move on. Excellent, good. So now we continue. They say 2. The resulting magnetic field when the current carrying conductor in A part 1 is placed between the magnetic field. Good. So remember, you have your magnetic field here. So your magnetic field goes from north to south. You go back to the notes, so you can see what I'm talking about. So this is similar to this part of the lecture here. You see it? This is what's going to happen. You have your magnetic field here. and the magnetic field going to cause it to want to move. So if we go back, right, if we go back to the notes, the sheet here, let us not close this. If changes, no. Right. So they ask us to draw the magnetic field around that. How are we going to do that? Simple. Um, so you have two magnets, N and S. So you have this here. So you're going to draw one, and then I'm going to draw it like this. You're going to draw a magnetic field. So your magnetic field would be like this. The lines wouldn't touch each other. All right, so I'm just showing you how the notes is, so you have an idea. So it's ready like this here, which would try to force the conductor to move downward or upward in whichever scenario. All right, so good. Good. So it's gonna be something like that, but it will cause this to want to go down. Let's fix this part here. All right, so something like that or similar to that. Good, so that's where drawings of so well, not exactly like this, but much neater than that. All right, everybody okay with that? CXC, you okay with that so far? Good, nice. So we're moving on to the question now. This is a question here which is similar to the transformer, like the motor. Sorry, it said here, Figure 7 shows the end view of a DC simple motor. Good. Labeled here are the parts of the motor. Which part is labeled X? Let me go back. Wonder if I have any others. Yeah. This says what? This is a part of the motor. This is the labeling. It is the commutator. So your answer for this is commutator. Good, nice. So commutator, good. Excellent. So commutator is your answer for that. So we're moving on. Now they said explain. That's this question short. So right. So they explain what happens when the switch is closed. Right. Your answer should include the direction of the current, the force acting, and any rules applied to the direction of rotation and how continuous rotation is achieved. It's 9 marks, is plenty explanation. So we are talking about the forces that act the direction of the current and the direction of rotation and what rules. So which rule the motor operates on? Fleming's. We go back again for you to see. Fleming's left hand rule. So we know that for sure. Fleming's left hand rule is what we're using. So we're talking about a rule. So we're going back here. So when your switch closes, normally I start it like that. When switch closes, when switch is closed, when switch is closed, comma, what happens? Current goes from which direction to which direction? Hmm? Let me go back. Just wait to see the symbol for battery. Um, wonder if I have it in the lecture, boy. Yeah, I think I'd given all of that. Right. This is the symbol here. So this is our cell, and the negative part is which one? The small or the the large? The small or the large one? Hmm? Let me show that because way to understand. So your negative is the small terminal. Watch here. Your negative is your small terminal. Mm, Alright, so your negative is a small terminal here. So current goes from what? Current flows from positive to negative or negative to positive. Hmm? Let's see from a lecture here. Right, so this is your positive and this is your negative here. So current will go from positive to negative. So we're showing from this direction here. This is a positive. When current switch close, current flow through this side. So this is going to be a positive here. This side must be bracket there. So here going to be a positive side, and here going to be a negative. Everybody seen that? Wait, must see if I fix that better. Alright, so this is your positive side. So current will flow through the circuit, and part of a commutator going to be positive, part going to be negative. So we continue with it, so when the switch is closed, current flows through conductors to the commutator Then current flows now, so it goes through the commutator, current flows from D to C, flows from D to C, so it goes through D to C, current flows from flows to the commutator, then from D to C through C to B, C to through C to B, and then back to B to A. Good? So that's how the current flow. So now remember that your magnetic field always goes from, since the magnetic field field goes from N to S, which is north to south, comma, and the magnetic field created and the magnetic field created and the magnetic field the magnetic field created in the current carrying conductor between points point D and C slash between points D and C, right? Between point D and C using Fleming's left-hand rule. So if you place Fleming's left-hand rule with your current placing in direction between B to C, your forefinger showing moving from N to S, your thumb would point downward. Good. So just showing you back from this here. From here, from our notes, using Fleming's left-hand rule, but you're placing now your thumb, like your thumb going into between B and not your thumb, sorry, your middle finger going from C to D, D to C, sorry, in the direction of current flow. Your forefinger points from N to S, your thumb would point downward. So one side would go downward and one side would go upward. All right, just as shown in this diagram here. So here, using left hand rule, the interaction between both magnetic field causes the conductor to move at point D to C to move downward. Same thing gonna happen now. So one gonna move downward and one gonna move upward. Same thing gonna happen now. Interaction between both magnetic fields will cause the conductor between points what was the other point, B and A, between points B to A to move. Interaction between magnetic field will cause the conductor between points B to A from whatever based on Fleming. So based on Fleming's left hand rule, the interaction between magnetic field will cause will cause the conductor between points A and B to move downward. Good. So one, sorry, not downward. They're going to be upward. My mistake. They're going to be upward to move upward. So one moving down, one moving up, so which will cause a catapult effect, as was shown here in this diagram. Just showing you here. So these two forces in opposite direction constitute a couple, which produces a turning effect. Good. So using back that same thing. So these two forces constitutes to a forces in opposite direction constitutes to a couple which produces a turning effect, which produces a turning to make coil rotate. Then this rotation will be in a, so if points A to B go up and point C to D goes down, that's a clockwise direction. This rotation will be in a clockwise direction. Right, GC students, CXC students, you get that so far? Continuous rotation of the loop of the of the loop of the coil, sorry, continuous rotation of the coil is occurs because the commutator allows only unidirectional current flow to the loop. Unlike the AC motors where you would have slip rings, in DC motor you only have commutators which would allow it to flow in only one direction. Good, so we covered all the aspects of your answer. CXC, this is clear to you? The solutions are posted? Good. So for homework CXC, um, you have to do for me, pages pages 5 to 9. CSEC homework, pages 5 to 9. Good, so work on that for next week. Just putting back up the solutions here. Once you're okay with it, just let me know so I could take it on. You could abbreviate it in simpler terms and write it into more eloquent composition so that you could understand when you're learning. All right. Once you're okay with that, I will just shut down. So again, so for next week class students, we'll be going through the homework. So every class, every examiner body have as IGC students have homework, C6 students have homework. Next week topic would be based on, because we come at the end, so by May we should be complete atomic structure. So next week we're doing atomic structure, which is fairly simple. So you do that and start a topic on radioactivity, and we would not complete radioactivity next week. However, the following week we will complete it. Remember, we have 2 sessions every week, one on Tuesday and one on Tuesday. Friday, sorry, 5 to 8. So next week we will do atomic structure. So as class start next week, we'll do the homework here. Any problems, please highlight them so I can touch on them next week. For the following classes that gone by. We do the homework first and then do atomic structure, which would lead into radioactivity. Because radioactivity is a big part in both CSEC and IGC exam papers. Okay. So everyone okay with the with class today? We pass paper solutions and how to answer them. Good, excellent. So thanks for tuning into class today. I hope you have enjoyed today's class. See you next week, Tuesday, 5 p.m. to 8 p.m. Make sure get the homework done, and everybody be safe again. And please follow preventative measures to avoid getting this coronavirus. Enjoy your night and be safe. Take care.